Welcome to the pre-recorded lecture of 18th September 2020, and we will continue discussing well log interpretation. So far what we have discussed is around gamma ray, and we have said that from gamma ray signals we can distinguish between sandstone and shell. We said that the lower gamma ray, like here it is presented, lower gamma ray represents a sandy section, and then higher gamma ray represents shelly section. We said how a coarsening upward sequence looks like, how a fining upward sequence looks like. We also talked about how we can calculate net to gross. So there is another uh, type of log which you can use for your distinction between shell and sandstone is spontaneous potential. And here you can see the spontaneous potential is given by this. So this is referring to the first panel that we are looking at right now. You can see here this bold black line represents the variation of spontaneous potential with respect to depth. And you can see that some places the spontaneous potential is higher, some places spontaneous potential is lower. And so like gamma ray, higher spontaneous potential also corresponds to shelly section. So you can cross check. So the corresponding depth here is also the corresponding depth here. You can see from the gamma ray signal, it looks like it is shelly, but from the spontaneous potential, higher spontaneous potential corresponds to shelly section. Here also you can see the sandy section is reflected in the spontaneous potential curve, and so on and so forth. So both from spontaneous potential and from gamma ray, you can calculate the net to gross, as well as you can essentially distinguish where are the places where you will find sandstone and where you will find shell. Okay. Now, although you can see that the resolution of the spontaneous potential curve is slightly lower than the gamma ray. What do I mean by that? For example, you can see here within this shell package, there is a little bit of a negative peak, which will correspond to a small sand streak, but that is not being fully picked up by the spontaneous potential signal. So the resolution is slightly less, but spontaneous potential can also be used to determine the uh, sandstone sections from the shelly sections. Okay, so that distinction is possible. Now, what spontaneous potential essentially records that you have two electrodes. So let me just take the liberty to use the whiteboard. So, for example, if I have, this is my well. Okay, I have two electrodes, maybe one here, another here. Okay, and you essentially calculate the potential difference. Okay, calculate the spontaneous potential difference. Okay. So in case of shell, the potential difference is higher, and in case of sandstone, it is slightly lower. So that's how we have distinguished between sandstone and shell. Now, the next curve we are going to talk about is resistivity. So if I ask you, sorry, that I have two sandstone units, the sandstone unit A and sandstone unit B. Remember, both are sandstones. Maybe the sandstone unit A is filled with hydrocarbon. This is filled with hydrocarbon. And sandstone unit B is filled with water. Okay. Water means brine, right? Okay. Brine means, so water, brine refers to water plus dissolved salt, right? So which one will be more conductive, the brine or the sand, the hydrocarbon? And you can, from your electrochemistry class, you very well know that this is an organic product, so it's not ionic. The brine, the water, when it contains salt, it can ionize very quickly. So of course, hydrocarbon, the one that contains hydrocarbon will be more resistive, and the one that contains water will be more conductive. Okay. So now, if I look at a graph panel, let us say first I am drawing. So the first panel, so this is my TVDSS, for example, and first I am drawing my gamma ray curve. By looking at this, I can simply identify, and then say, for example, I am looking at, so this is gamma ray, and then there is another panel where I am looking at resistivity. Resistivity curve looks like this. Okay. So we are not that much concerned what happens in the shelly section. So first thing that we will do, we will distinguish the sandstone section. So this is my sandstone section. This is the top sandstone, top of the sandstone, and this is the bottom of the sandstone. And that I have distinguished from my gamma ray curve. Okay, now I am looking at the resistivity curve. So within that sandstone, I can see that up to this depth, let's use another color. So up to this depth, yeah, the resistivity here is higher, the resistivity here is lower. So that will give me a direct understanding that perhaps the fluid that is present in this part of the sandstone, okay, this is perhaps hydrocarbon, okay, either oil or gas, we don't know, it can be either of them, okay, but I have a higher resistive fluid within this sandstone. This is perhaps hydrocarbon, and the bottommost part, although this is sandstone, but the resistivity units are less, so this is perhaps water. Now, this is the contact between hydrocarbon and water. This depth is called FWL, free water level. More specifically, okay, this can be GWC, gas water contact, or OWC, oil water contact, either of them. In general, it is called free water level, and more specifically, it can be a gas water contact or an oil water contact. Now, if we come back to the actual example, you can see here. So this is my resistivity curve. This is my resistivity curve. This uh, black one, solid black one. Okay. Don't be bothered about the dashed line, which we are not discussing it at this moment. So this is my resistivity curve. So if I ask you which one is my sandstone section, let's take a snip and explain. So let us just take the spontaneous potential and the resistivity. From spontaneous potential, we can also distinguish sandstone and shell. Now, if I am here, so if I ask you to pick up the sandstone units, then you can say that this is one sandstone unit. with a little bit of shell in between. Here is also a sandstone unit. Here is also another sandstone unit. This is one unit of sandstone. This is the second unit of sandstone, the third unit of sandstone. And you can see, let's just right now focus on the first unit. You can see that the resistivity, so up to here, the resistivity is pretty high. Okay? And then the resistivity actually decreases. So this part of the reservoir, this step interval, is perhaps rich in hydrocarbon, right? And then the rest here is perhaps water. And so this is my seawater level. So you can do that exercise here as well. You can see here there is not much of resistivity. So these are perhaps also filled with water. Okay, these sandstones are also filled with water because the resistivity value, as you can see, is not very high. Here you can see the resistivity values are not very high. So this is perhaps these two sands are also water rich. Is also water rich. But here at the top part of the sandstone, I have hydrocarbon. So as you can see, this is my sandstone interval. This is my free water level. Now, from the resistivity curve, like from gamma ray curve, we could actually calculate. The net to gross. Similarly, from resistivity curve, we can calculate, your hydrocarbon saturation. Hydrocarbon saturation. The formula for calculating hydrocarbon saturation is root over Rho by RT, where RT represents the formation through resistivity, is the reading from the deep induction curve in the zone of interest. We'll explain what it is. And Rho is the reading of deep induction curve in the clean, non-shelly formation, fully saturated with water. So, moral of the story: RT is the uh, is essentially the resistivity in the hydrocarbon zone, and Rho is the resistivity reading in the water zone. Okay, so if I do an exercise, it will be clearer. Say, for example, I want to calculate the SW at this location, okay, where this red line is given. Yeah, this maroon line is given. Say I read the resistivity value, okay, which is RT is equals to 30, and then I have identified this to be my fully watery zone. Okay, and here they have taken actually taken the dotted line. So dotted line also represents the resistivity curve itself, but this is a more penetrative resistivity curve. It goes way inside the formation. So there are two types of resistivity curve. One we call as the shallow resistivity curve. The other one we call as the deep resistivity curve. So that this dotted line is essentially the deep resistivity curve. This measures the resistivity deep inside the formation. Okay, and the shallow resistivity curve measures the resistivity at a shallower interval. Okay, so we have taken the deep resistivity curve for this example. Okay, so we can calculate at zone 1, which is this one, okay, which is the purple, the red zone. Okay, and we have got the value of RT is 30, and in the water zone we have got the value of R0 is essentially 0.3, which is here, this blue line, and in the zone 2 the value of RT is 2. So we can actually calculate in the zone 1 using this formula, the water saturation is 10%. That means the hydrocarbon saturation is 90%, right? Because SH is equals to 1 minus SW, right? You remember? So the hydrocarbon saturation in the red zone is 90%. Similarly, the water saturation in the zone 2 here is around 40%. Okay, so that means the hydrocarbon saturation is around 60%. So that means, in physical terms, that 90% of the fluid present in this zone, in this red zone, is actually hydrocarbon. And in the blue zone, it is almost 100% water. There is no hydrocarbon, almost no hydrocarbon, or insignificant amount of hydrocarbon. And in zone 2, we have around 60% of hydrocarbon. That is how you can calculate hydrocarbon saturation. Now, there is another type of curve which we called sonic curve. And from sonic curve, what you can do, you can calculate the porosity. Okay? So, and porosity essentially is calculated using this particular formula. Delta T minus delta Tm divided by delta T liquid minus delta Tm, where delta T liquid and delta Tm are the transit times in the pore liquid and rock matrix respectively. The sonic log investigation is limited to the invaded zone. The mixture of liquids in the rock pores is usually assumed to have a transit time. Delta T liquid is 189 seconds per feet. Selection of the matrix level time delta Tm is based upon the knowledge of the lithology of the section log. Commonly used delta Tm values are these. If the rock is unconsolidated, sandstones found in the South Louisiana, for example, that's not important. The delta T used is 55.5 microsecond per feet. Okay, so I will explain what is a sonic log first, and then I will explain what is the philosophy of calculating porosity from there. Okay, so what in sonic log people do, suppose this is my well. Okay, and then suppose we want to investigate the porosity of this particular zone. Okay, so what I do, I first create with a probe a small earthquake here. Okay, and then I receive this acoustic signal. Okay, with another, so this is my source, this is my receptor with a receptor here. Okay, so the sound wave essentially will travel through this formation, and it will reach from source to the receiver after a time delta T. So this, a sonic log essentially shows you, a sonic log essentially shows you the variation of delta T with respect to depth. In some cases, the delta T will be higher, in some cases, the delta T will be lower, and so on and so forth. So that is my sonic log. Now, what is the philosophy of calculating um, what is the philosophy of calculating porosity from the sonic log? Okay. Now let us imagine that I have a box. Okay, and this box is fully saturated. I have a simple box. Okay, and this box has, for example, water. And then I, send a sound wave here. This is source, and I receive my sound wave here. This is a receiver. Okay, and I measure my delta. Now, so this first instance represents a situation of, this is 100% porosity, you know, 100% porosity. That's everything is empty, and I am sending my acoustic wave from source to the receiver. Okay, and because it is 100, because it is completely filled with water, that means it is 100%. 100% porosity. Now, say for example, I have a block which is completely filled with sandstone, and it has no porosity. It's completely filled with sandstone, no porosity, 0% porosity, 0% 5. This is my second case. Okay. And then also I have a source and a receiver, and then I measure the delta T. So this is what we refer to as delta T liquid, and this is what we refer to as delta T matrix. And then, for example, I have a box which is filled with, say, sandstone, and then I have like 30% porosity. And then, so there will be, now if I have a source and a receiver, and if I send my sound wave, that will have another delta T. So now comparing this delta T with delta T liquid and delta T matrix, I can simply know what percentage of porosity, I can guess what percentage of porosity is present in this box. Okay, so that's exactly what is being done here. Okay. So delta T is the measured porosity and at any formation. Measured transit time between any depth interval, and then delta T matrix is the matrix porosity. Say for example, I am doing my test in the sandstone, so I will use the delta T value between 55 to 51 microsecond per feet, and then delta T liquid is where it is completely filled with a fluid. So that represents 100% porosity. So 100% porosity delta T minus 0% porosity delta T. That is my that is in the bottom, and at the top we have the delta T that I am measuring and the delta T of the matrix. I mean 0% porosity. So if we do that calculation, we should be able to calculate my porosity. Say for example, I try to calculate porosity in this interval. Okay, so this is sandstone. Okay. So the delta T. So this is say for example, my reading is 90. Okay, the reading is 90, and for delta T matrix, because it is sandstone, I am using 55.5, and delta T liquid, as I have said, is around 189, and delta T matrix is again 55.5, and by doing this, I can calculate the porosity to be around 26%. Okay. So the idea is to look at my transit curve here, and then see, say for example, I want to calculate my porosity at this point. Okay, so what I will do, let's take a snapshot and explain. Suppose I want to calculate my porosity at this point. Okay, so I measured my, what is the transit time here, whatever it is, say 50 to 150. So this is perhaps a value of, I don't know, say 80, okay, whatever. So that is my delta T. So, but this is again the sandstone unit, right? So my porosity phi will be 80 minus 55.5, because that is the delta TM matrix, because it is sandstone, and then this is 189, whatever the value is, right? And then we can calculate whatever percentage of porosity. So from, if I now recap very quickly, so from gamma ray, have calculated net to gross, from resistivity, I have calculated my SW, and SH will be 1 minus SW. And from gamma ray, actually, we have calculated V shell. Remember, we don't calculate net to gross directly, and net to gross is equals to 1 minus V shell H. And then from sonic, I have calculated porosity phi. Okay. So if I have these three, if I want to calculate STOIP, if I know my GRV is my gross rock volume, the total volume of the rock, GRV, that stands for gross rock volume. So this is my rock, right? If I calculate the volume of this rock, that's my gross rock volume, which is nothing but area multiplied by thickness, multiplied by porosity that I get from my sonic log, multiplied by SH, which I got from my resistivity curve, multiplied by net to gross, which I got from my gamma ray curve, okay, multiplied by, of course, 1 by Bg. That's my gas expansion or oil expansion factor, which depends on the density of the oil and gas. Okay? But that is generally readily available value. But from these graphs, okay, what I'm calculating porosity, I'm calculating hydrocarbon saturation, and I'm calculating net to gross. And gross rock volume we generally calculate from seismic, which we will discuss later on. Okay? How from a seismic image, gross rock volumes are calculated. Okay? Now, the final kind of curve I want to show you today is called is actually a combination of two curves. Okay? One we call as the neutron porosity, and the other one we call as the density. Now, if you see here in this particular graph, you see here, this is the gamma ray curve, right? So from the low gamma ray, I have discovered my top reservoir, and this is my bottom reservoir, right? Reservoir's top and reservoir's bottom. And then from higher resistivity, and then flipping to lower resistivity, I know that this is my seawater level. Now I want to distinguish, and this is hydrocarbon and this is water or brine. Okay. Now I want to understand whether this hydrocarbon is oil or gas. And for that, I look into two more curves together actually. One we call neutron porosity and the other one we call as bulk density. Now you see, first I want you to focus on the scale of these two graphs. You can see for neutron porosity, this becomes, so this is the lower end of the spectrum and this is the higher end of the spectrum. So it increases this way. And then the bulk density increases in the opposite direction. Now let us see here at the very top part. So now you can see here that at the very top part of the hydrocarbon column, the bulk density becomes lower. So for the very top part, and then the porosity also becomes lower. Neutron porosity also becomes lower. So, and then there is a quite a flat separation. And this is what we call as neutron density crossover. And such large neutron density crossover is typical representation of gas. So this interval is perhaps filled with gas that you cannot distinguish from the resistivity curve. That you can distinguish only from the neutron density curve. Okay. How neutron density curve actually works, we will discuss later. Actually, this will be a part of one of your assignments you will do, but we will understand the mechanism later on. But for the time being, remember that this neutron density crossover typically suggests that the type of hydrocarbon is actually gas. And then you can see that after the crossover is over, you can still see I am in the higher resistivity zone. Okay, so that refers that the rest of the higher resistivity zone is perhaps oil, and then comes your water. So in this whole fluid column, I have three types of fluid. The first, the topmost part, which is the least dense part, is actually is gas, and then comes oil, and then comes water. So this is actually my OGC, that means oil gas contact, and this is my OWC, that is oil water contact. So, and this is also, we will call it as free FWL, free water level. Okay, and then from here my shelly stuff actually starts. So if I again try to, if I again uh, try to recap what we have discussed so far. So we have discussed about basically few types of logs. So the first one we have discussed as gamma ray. The second type of we discussed spontaneous potential. Third, we discussed resistivity. The fourth, we discussed as a combination of sonic, and fifth, we discussed as a combination of neutron density, neutron, neutron porosity and density. So gamma ray would help me to calculate net to gross. Spontaneous potential will also help me to calculate net to gross. Resistivity will help me to calculate SH or SW. Sonic will help me to calculate porosity. And neutron density will help me to calculate whether is oil or gas. Okay, whether the type of the fluid is oil or gas. Okay. Now there are plenty of uh, other types of logging logging logs. For example, okay, we have NMR log, okay, and then we have image log, etc. So now these are the must-have logs. Okay? These are the must-have logs in any well. And these are like optionals. So I will send you an email with uh, dividing you amongst groups, okay, and assign you to make a presentation on different topics, not only related to well logging, but also related to different behaviors of wells. So there will be a assignment announcement soon. Where you will be asked to be, so I will make the groups. This will be a group assignment where I will put you into some groups, okay, and where you will discuss amongst yourselves and prepare a presentation and record a video with your presentation like I do for classes, okay, and share it with me. And then I will, for each group, I will assign a particular topic which will be related to wells that will include some of the aspects of the well log as well. Okay, and then you have to share that presentation with the video recorded like we present these classes. You can actually have a Google meeting amongst yourselves and record the presentation. All of you have to present, okay, on different aspects of wells. But I will announce that assignment sometimes next week. All right, so I stop it here, and we will. I'll see you next week. Thank you very much.